All right, so let's go ahead and take a look at this problem. We actually did the Kahoots on this today, and I just want to make sure that we are solving things correctly, going through the solution, making sure that you feel comfortable with what we're doing and how we're getting it done. So, the first question, and let's just kind of notice some things here. We really got a lot of information here for these coefficients of friction, but let's talk about what's going on. So we have this car, and when I say car, I'm thinking a situation like this. It's a kid's car. There's the kid in the car. It's got real tires, but it's actually stuck. And so what that means is we actually have to push this car, and the wheels are not rolling, so it's a little bit of a different situation than a car just rolling on the pavement. So when we push the car, we want to know if it's going to have an easier time moving on wet or dry pavement. So let's actually look at this. So the car is stuck, it's not moving, and we want to get it moving. So what that means is we need to look at the static friction, that's for things that are not moving. And we notice the dry pavement static friction coefficient is 0.9, and the wet pavement coefficient of static friction is 0.8. Now let's remember that friction is mu times the normal force. So if mu static is bigger than mu kinetic, that means, if mu static on the dry pavement is compared to mu static on the wet pavement, what we're seeing is that the wet pavement is actually not as big coefficient of friction. So what that means in real life is the friction on the dry pavement is bigger than the friction on the wet pavement. And that means it is actually easier to move on the wet pavement. Now let's take a look at the second problem and see if we can use these coefficients in a similar way. So we have wet pavement that we're trying to start the car moving on, so that means we need mu static for the wet pavement. And then we want to also look at what happens when we keep the car moving on dry pavement, so we need mu kinetic for dry pavement. Now to determine if the car is going to move, we need to see, we need the force of pushing to be bigger, just a little bit bigger, and in this case equal. So we'll just say about equal to the friction force. So that's going to be balanced, and that's going to be mu static on wet pavement times the normal force times mu, and here it's going to be mu kinetic on dry pavement times the normal force. Now let's compare these. Since mu static on wet pavement is 0.8 and mu kinetic on dry is also 0.8, it turns out these two forces are actually equal. So it's equally difficult. So the answer here, we're going to say, is it's actually equally difficult. And for number 3, assuming the weight of the car is 550 newtons, what is the force of friction? Let's actually draw the free body diagram. So we've got the normal force, we've got the weight, we've got the engine force, and we've got the friction force. Now since we're moving at constant speed, that means the engine force balances the friction. We know the normal force balances the weight, and we know that friction is mu times the normal force. Friction is fun. So let's see if we can actually calculate what the force of friction is. Well, I don't need to know what the engine force is. Let's look at the normal force. So I know the normal force equals the weight, so that equals it to 550 newtons. I know friction is mu times n. So friction is going to be 0.7 for moving on wet pavement times 550, and so I'm going to get 385 newtons. And for number 4, how hard does the brother have to push to keep the car moving at that constant speed? it's going to balance. Constant speed means the pushing force. So we don't have the engine working. I should have been clear on that. We have the pushing force of the brother pushing the car. So the pushing force balances the friction, which is 385 newtons as well. And for the next one, how hard is the car pushing back on the brother? 385 newtons by Newton's third law. And let's remember what Newton's third law actually says. In fact, I want to type it out just to be clear. What Newton's third law actually says is if if the brother pushes car pushes back on brother with equal force in the opposite direction. So that's how we're getting that answer. And why doesn't the brother go flying backwards under this force? Let's be clear. He would go flying back, but friction keeps him rooted to the sidewalk, to the wet pavement. So that's pretty much it for this problem set that we did on Kahoots, but I wanted to make sure you had a full solution.